let's focus our attention on something that's very relevant in as far as quantitative aspects of chemical change, which has to do with purity. Sometimes we would express this purity in terms of a percentage in the context of, reactions that involve, substances that have got impurities. So what exactly is purity all about? Some of the key words that we would want to actually pay careful attention to is purity, which also we've indicated that we can express it as a percentage. But in what context is, purity relevant in as far as the chemical reactions are concerned? Okay, so we know that most samples of substance, they contain impurities. Now, if you ask yourself, the most important question, that what are impurities? Suppose you've got a substance, when you find it, in the manner in which it occurs, it's not 100% that pure substance. It may have some other substances which are not exactly, the main, substance. As a result, we'll say that this substance is impure. This could be, in the context or in the example of mineral ores. When you purify minerals, especially, say, in the mining sector, they actually try to get rid of the impurities so that at the end of the day, we remain with the, the actual substance without these impurities. So in terms of the pure substance in the sample, as expressed as a percentage in terms of the total mass, that gives us a percentage purity of a substance. So we want to think of it that way, right? So these samples, they contain impurities. Minerals, they contain impurities even after the refining process. So the mass of the pure substance can be expressed as a percentage of the whole sample. This is what gives us the percentage purity, right? So it's a simple and straightforward question, but concept. However, it is understood in the context of chemical reactions. So how do we calculate percentage purity? It's actually the mass of the pure substance in the sample divided by the mass of the sample multiplied by 100. So this is the mathematical, equation that we use to determine percentage purity of a substance, right? So how exactly do we determine percentage purity? Given the mass of the sample or the impure reactant, why is we saying reactant? Because it could be in a chemical reaction, okay? So we need to complete a chemical reaction and measure the mass of the products formed, okay? So the product is assumed to be 100% pure, right? And then we can carry out the stoichiometric, now working backwards, the stoichiometric calculations to actually find the mass of the pure reactant based on the mass of the pure product. And then a comparison is made, between the mass of the reactant to the mass of the pure, product as a percentage. Okay, so that's as far as how we determine percentage purity. Here's a simple and straightforward example just to give us an idea of what we mean when we say, okay, these are the steps as to one that needs to follow in as far as calculating percentage purity. We've got a sample of eggshells, okay? So eggshells, they contain, calcium carbonate. They contain calcium carbonate and other substances. Okay, so we are interested in determining, the actual percentage of calcium carbonate in the mass of the whole sample. So the total mass of the sample is 5 grams. It's heated at a temperature of 100 degrees Celsius, and it decomposes. What does this tell us? It tells us that this is a decomposition type of a reaction, okay? So step number 1, we need to balance the equation of reaction. How many atoms of calcium do we have on the left? It's 1, 1. Carbon, it's 1 on the left, 1 on the right. Oxygen, we've got 3 on the left, and then 3 on the right. So this is actually balanced, okay? So the stoichiometric ratio in which they react is 1 mole of calcium carbonate decomposes to form a mole of carbon dioxide and a mole of calcium oxide, right? So if the equation is balanced, then we measure the moles of carbon dioxide formed, okay? The moles of carbon dioxide formed in this case, we are saying that if 5 grams is heated, so how many moles of calcium carbonate are there in the 5 gram sample, okay? So number of moles of calcium carbonate, okay, is equals to the mass of the sample over the molar mass, okay? So we'll determine the number of moles of calcium carbonate in the sample. And then we are also told that we need to measure the moles of carbon dioxide, okay, that is formed. So if we have the moles of carbon dioxide that are formed, okay, whatever that is, we'll try and work backwards to say how many moles of calcium carbonate actually produced this mass of this moles of carbon dioxide, and then actually get to a point where we are able to determine the actual percentage of of calcium carbonate in the sample of the eggshells. So step 3, and then we work backwards, we determine the mole of calcium carbonate needed to release that amount of carbon dioxide, okay? So it's like we working backwards, but the idea is, the idea of number of the moles of substance equals to mass of sample over the molar mass is what is central here, and the stoichiometric ratio of 1 is to 1 is to 1. So we would ask ourselves to say a mole of calcium carbonate produces whatever number of moles of carbon dioxide. So given the moles of carbon dioxide, we can work backwards and determine how many moles of calcium carbonate were responsible for producing that amount of carbon dioxide. And then we can, after that, we can determine the mass of pure calcium carbonate in the sample. So at the end of the day, percentage purity of this sample of calcium carbonate is equals to mass, okay, of calcium carbonate, okay, in sample, right, divided by total mass of sample. All right? Okay, as a percentage, we multiply this by 100. It will give us the percentage purity, right? So that's the main idea in as far as, determining the percentage purity of a substance. For now, let's take a short breather. When we come back, we'll try and look at a practical example with the actual, masses of samples and try to determine, the percentage purity using, real substances and real, masses, and try to work backwards in as far as the stoichiometry is concerned. Let's take a short break for now.